Hello everyone, myself Deepa Singh, working as assistant professor in Suresh Gyan Vihar University. Today we discuss about different methods or different techniques how you enhance the solubility of particular drug or particular formulation, and why this solubility enhancement is needed for formulation, and role of surfactant for solubility enhancing, and different types of surfactant including HLP scale and their application, and how affect this surfactant to a particular drug for enhancing the solubility. So let's start this topic. And in this topic, first we covered learning objective, and learning objective. Students should be able to understand this topic before starting this topic. Different methods of enhancement of solubility, which technique or which method we use for enhancing the solubility, surfactant and its classification with example, different types of surfactant, including example or by particular surfactant to select, and in this HLP scale and its application and role in the solubility enhancement of particular surfactant, and why you select that particular surfactant. All this comes in the surfactant parameter, and in this these are the general method or increasing techniques used for enhancing the solubility. And in this, first is addition of a co-solvent, pH change method, reduction of particle size, and the temperature change method, hydrotrophy, addition of a surfactant, dielectric constant, and compensation. These are the technique or major technique. By the help of this technique, you can enhance the solubility or increase the solubility of particular drug. And according to this type of formulation, select particular method, and it may be in a combination also, not a single method is used. You can also use a combination for enhancing the solubility. In this, first addition of a co-solvent, in this mainly use co-solvent. Co-solvent may be any type of a solvent which enhance the solubility of a particular solution or particular drug. And when you use the add this particular solvent, it show more solubility. So in this, weak electrolytes like phenobarbital type of class drugs, and non-polar like nitrocellulose, these are poorly soluble in a given solvent, and for such poorly soluble material, to enhance their solubility, the water miscible solvent are used in which drug has a good solubility. Suppose these type of a drug, or those drugs which have a low solubility or poorly insoluble. So in this case, you use some another solvent or co-solvent to enhancing the solubility of particular drug or particular formulation. And in this process, is improving solubility is known as co-solvency. The solvent is used as co-solvent. In this technique, the particular solvent that you used is known as co-solvent, and this overall technique or overall process is known as co-solvents, because you're using some solvent. That's why that particular solvent that you use for formulation and enhancing the solubility is known as co-solvent. And in examples, phenobarbital is insoluble in water. A clear solution is obtained by dissolving a mixture of alcohol, benzene, propylene glycol. Suppose you are dissolving phenobarbital in water, then it is poorly soluble, maybe completely insoluble in water. But you take a solution in a maybe alcohol, glycerin, propylene glycol in an individual way or maybe in a combination way, it enhances the solubility of phenobarbital and forms a clear solution. And co-solvent are like polyethylene glycol, glycerin, sorbitol, PEG, glycol formol, glycopyrrole, ethyl carbamate, ethyl lactate, and dimethyl acetamide. These are the all solvents which we use for enhancing the solubility. You select this solvent according to type of formulation, according to type of the drug, which drug you require to enhance the solubility. So all these about co-solvency. Next is pH change method. In pH change method, weak base like alkaloids, local anesthetic, and weak acids like sulfonamide and barbiturates are these drugs which show insoluble or less solubility. So due to this less solubility, you need to enhance their solubility with the help of changing pH, or maybe little amount of buffer or pH solution you added, so that that particular solution get changed or show more solubility compared to the previous one. In this aqueous medium, they dissociate poorly, and dissociate portion is insoluble, like benzoic acid and phenobarbital. And so solubility of undissociated portion is improved by pH control method. For weak acidic drug like increased pH, solubility is increased. For weak base drug, decreased pH, increase the solubility. The selection of a proper pH is also dependent on type of formulation, which type of a drug you use, and you maybe add or maybe remove that particular pH, or by increasing or decreasing the pH. Every drug have a different property, and it require different pH conditions. Suppose you taking a weak acidic drug, so In this condition, you increase the pH level, or you add more pH, acidic pH, so you can increase pH. And if you increase the pH, it will show more solubility. But it's vice versa for weak phase. Means if you decrease pH and solubility is increased. And so the selection of the proper pH is also dependent on type of the drug and which type of drug it is. And when you add this proper pH condition, then it will be dissociated to show more absorption rate or good dissolution rate. And so you can change the solubility of particular drug with the help of pH change also technique. And in this reduction of a particle size, improves solubility of a drug. Basically, reduction in particle size increase contact surface area of the particle, and thereby ultimately it increase the rate of solubility of the drug. In reduction of the particle size, if you reduce particle size, if the particles are a small size, they show more surface area and easily solubilize. So this reduction of the particle size is also responsible for proper solubility or good solubility, because large particle take more time to solubilize, or because it's a more surface area. So less surface area, or due to the large size, it do not dissolve or do not solubilize easily. So you can reduce the particle size of convert it into fine particle. Therefore, due to the small particle or fine particle, it show more surface area, and due to more surface area, it easily spread out or show more solubility. This is all about reduction of particle size. So reduction of particle size is also responsible for good solubility or good solution of the drug. And next is temperature change method. Temperature change method is also responsible for enhancing the solubility. Only the temperature increasing technique is not used. You can also decrease the temperature. Means not necessary that all drugs are dissolved in particular heating condition. Some drugs are dissolved in a cold condition also, or maybe at cold climate. You can reduce the temperature so it can be easily dissolved. So temperature change method is also one method to enhancing the solubility. When you change your particular solution temperature, it gets easily dissolve or show more solubility. And this mainly two reaction are responsible: endothermic reaction and exothermic reaction. In endothermic reaction, by increasing the temperature, solubility is increased. In endothermic means when you increase the temperature, enhance the temperature, and maybe it get show more solubility at a high temperature. But in case of exothermic reaction, by increasing the temperature, solubility is decreased. But it's just opposite to endothermic. In exothermic reaction, temperature is increasing and solubility is decreased. Means you do not rise temperature or do not increase the temperature. In this condition, require less temperature cooling condition to solubilize or show more solubility. Like methyl cellulose, when mixed with water and temperature is right, it becomes insoluble. To dissolve in cold water is added. And this one the example. Suppose methyl cellulose you add in a water and trying the room temperature to mixing, and after a particular saturation point you start heating. But this high temperature, the solubility or methyl cellulose don't solubilize, it show insoluble partner precipitate. But you dissolve this methyl cellulose in cold water, it easily solubilizes, show clear solution. So don't necessarily that heating temperature is required. Sometimes cold condition is also required to enhance the solubility. Next is hydrotrophy. In this hydrotrophy, the term hydrotrophy has been used to designate the increase in solubility in water. Various substances due to presence of large amount of additive, like solubilization of benzoic acid or sodium benzoate. In hydrotrophy, use some excipient or add some large amount of additives or other excipients. So in the form of more additive, this particular drug may be solubilized easily or show more solubility in water due to more solubilized compound or more additives. Like so, example is solubilization of benzoic acid with sodium benzoate. Benzoic acid show more solubility with the help of sodium benzoate. When you use this two benzoic acid and sodium benzoate in a combination, it show more solubility compared to individual one. Next is addition of surfactants. Addition of surfactants is also important parameter. And this is majorly used because it also show another property, or it enhance good amount of solubility. And according to different type of surfactant, it also available in broad range. And according to type of the drug, you select particular surfactant, which surfactant is suitable for your formulation. And in this, surfactants are molecules with well-defined polar and non-polar region that allow to aggregate in the solution to form a micelle, and non-polar drug can partition into micelle and solubilize. This surfactant technique is mainly depend on the type of surfactant and formation of CMC. You know that when you add surfactant at particular amount, it start forming CMC, and this one is known as critical micellar concentration. And in the CMC, aggregates of molecules are start forming. And when you enhance the surfactant concentration or enhancing the adding surfactant, this CMC form more and it show more solubility. But this is a fixed amount of surfactant you can add. But you add excess amount of surfactant, it may be show insolubility or less solubility also. So this surfactant is also helps to proper solubilize or enhance the solubility. Surfactant based in Taxol, that is solubilized in 50% solution of chromophore. This is an example. Next is dielectric constant. In dielectric constant, it is the effect the substance has when it is acted as solvent of the case, which is separate positively charged atom, like dielectric constant of water 80, and kerosene is 2, and glycerin is 45, and benzene is 2.2. These are the range of dielectric constant of particular solvent or particular compound. And this dielectric constant is also helps dissolve the solution or dissolve the drug in proper amount. And because this dielectric constant, there is a two charges or two electric constant which are oppositely charged. With the opposite charge, it show more solubility or interacted with each other. And due to interaction between two electric charge or positively charged particles, it easily show or maybe enhance the solubility. Next is complexation. In complexation, you form complex between the different excipient with the drug or use in a combination. So after complex formation or ligand formation, the molecular particular drug show more solubility. Like for complexation of a both drug and ligand molecule should be able to donate or accept the electron, and the solubility of a compound is sum of the solubility of a compound and its complex. Means in this ligand or molecules get interacted with drug, and both maybe donate or accept the electron, and this form the complex, and the complex of particular compound show more solubility and show more easily solubilized property. So in this example is aluminum mercury chloride is strongly soluble in water, and its solubility in water is increased by forming complex with potassium iodide. Suppose mercury chloride is react with potassium iodide, and after reaction it form water soluble potassium mercury iodide, that is K2HgI4. And when you react with this individually, it shows less solubility compared to the complex form. So when you form the complex within two compound or two molecule, it shows more solubility compared to individual one. Next is type of surfactant. In type of surfactant, first you know about what is surfactant. Everyone know that surfactant are the an active agent of which reduce the surface tension or show more solubility or interacted with each other. In the surfactant are the wetting agent that lower the surface tension of the liquid, allowing easier spreading and lower the interfacial tension within the liquid. Means surfactants are the wetting agent which lower the surface tension of the liquid and allowing easier spreading and lower the interfacial tension between the two liquids. Means surfactants are the main those agents which start wetting or reducing the surface tension or allow to easy spread or also lower or reduce the interfacial tension between the two particles. Due to reduction of interfacial particle tension, these molecules show more solubility or interacting with each other. There's different types of surfactants are available. Mainly there's two types, ionic and non-ionic. Anionic is one cationic, anionic and zizioteric. These are the three subcategory of ionic surfactant. According to type of the drug or requirement of the formulation, you select particular surfactant in solubility enhancement technique, and you can also take this surfactant in a combinations also. In this ionic surfactant, first one is cationic surfactant. In cationic surfactant, quaternary ammonium salt are more preferred because they are less affected by pH. Quaternary ammonium surfactants are largely used because they are good for your formulation and enhance good solubility and also show less interaction with other compounds. And This is also do not affect the pH range of particular formulation of particular drug. Cetyl trimethyl ammonium bromide (CTTB) and hexadecyl trimethyl ammonium bromide and other alkyl trimethyl ammonium salts, cetyl pyridinium chloride. These are the example of cationic surfactants. Next, in anionic surfactant, second one is anionic surfactant, and they are the most commonly used surfactant containing carboxylate, sulfonate, and sulfate ion. We discussed this. That first is cationic, second is anionic in ionic class. In cationic, mainly we use quaternary ammonium compound, but in anionic we use carboxylate, sulfates, and other sulfate ions. And sodium cetyl disulfate (SDS), ammonium lauryl sulfate, and other alkyl surfactants. Sodium lauryl sulfate, also known as sodium lauryl ether sulfate (SLES). These are the example of anionic surfactant that are majorly used. According to your formulation of drug, you can select any one or maybe the combination surfactant. And these anionic surfactants are largely used. Next is azeoteric. In this azeoteric, a single surfactant molecule exhibit both anionic and cationic dissociate. This is amphoteric or azeoteric. Means this azeoteric is also known as amphoteric surfactants. Also, another name is amphoteric surfactant because it have a both property. It will have anionic as well as cationic property. It have a both type of nature. So, if you require both type of surfactant, then you can go through this amphoteric category also. And the anion include carboxylate, phosphate group, and the cation include quaternary ammonium compound. And example of this azeoteric is dodecyl betamine, dodecyl dimethylamine oxide. Next, second category is non-ionic. Means in previous one we discussed ionic. Ionic is further divided into three categories: anionic, cationic, and azeoteric or amphoteric. Amphoteric or azeoteric both are same. And the second class is non-ionic surfactant. Non-ionic surfactant, these are the most widely used because they are free from non-compatibility, stability, potential toxicity, classified as a water-soluble, water-insoluble, non-ionic surfactant. And in non-ionic surfactant, you can say that it is a more compatible, more stable, and free from other toxicity or maybe water-soluble or water-insoluble. Non-ionic surfactant also means it's a good or more better than ionic surfactant because it shows less toxicity or more compatibility, more stability, and it can have both nature, hydrophilic as well as hydrophobic surfactant. Example of non-ionic is long chain fatty acid, fatty alcohol. These are the example of long chain fatty acid and fatty alcohol are the example of non-ionic surfactant. In this non-ionic surfactant, water solubility of these agents is further increased by addition of polyoxyethylene group through either linkage with one of the alcohol group like a SPAN. SPAN is also example of non-ionic category. When you use this, it shows more solubility or more enhancing solubility of particular drug. Next is HLB scale. According to this HLB scale, you can distinguish or find out which type of surfactant it is. If it is an ionic or non-ionic or having a OWO type. And this is showing particular range. According to range, you can decide which type of surfactant it is. And in this, in 1947 developed the system of hydrophilic lipophilic balance of the surfactant. And in this, the higher the HLB of the agent, the more the hydrophilic it is. Means Griffin in 1947 first developed this HLB scale. HLB is a hydrophilic lipophilic balance scale. And if HLB is higher, more the hydrophilic it is. If HLB value is more, then it means it's in hydrophilic in nature. It is a water soluble in nature, water loving nature. And the example is stream polyoxyethylene derivative of SPAN are hydrophilic and have high HLB scale, approximately 9.6 to 16.7. So you can say that if value is 9.6 to 16.7, having a more HLB value, and it's a hydrophilic in nature, and it is showing more water soluble property. And example of this hydrophilic surfactant is polyoxyethylene derivative or SPAN mainly. And if lower the HLB of the agent, more the lipophilic it is. Sorbitol, ester, and lipophilic have a low HLB value like 1.8 to 8.6. So you can say that if less HLB scale or small HLB scale like 1.8 to 8.6, it shows less water solubility or more lipophilicity or more lipid soluble in nature. And example of this 1.8 to 0.6 hydrophobic surfactant is sorbitol ester and lipophilic agents. And you select this according to type of formulation. If you require hydrophilic in nature surfactant, then you select an above scale HLB like 9.6 to 16.7. And if you require to select a lipophilic drug or lipid-soluble drug, that in case you can select a less or low HLB value scale like 1.8 to 8.6 because it shows more solubility in oil or it is an lipophilic in nature. And example of this lipophilic surfactant is sorbitol ester. And for hydrophilic or more HLB scale, example is polyethylene derivative and span. This is a diagrammatic representation of HLB scale. In this first 0 to 3 is most antifoaming agents. Then 3 to 6 is you can say that this is a 0 to 6 is antifoaming agent, and this 3 to 6 or maybe you can say that between 6 to 9 is WO emulsifying agents. WO emulsifying agents means water in oil in nature. Water in oil means water present in oil, or it may be lipophilic in nature or show more solubility in oil in nature. But you can say that this HLB scale 9 to 18 or maybe up to 15 show OW type, means oil in water, or it's contain oil in water phase and showing more water solubility or hydrophilic in nature. And between 9 to 15, you can say that is also a good wettability and spreadability agent. So in this category, hydrophilic plus wettability and spreading agent is also included. This is all about HLB scale. According to HLB scale, you can select any type of surfactant according to requirement. If you require antifoaming agent, then you select 0 to 3. If you require wetting and spreading agent, then you select 9 to 15 HLB scale. And according to solubility in a hydrophilic or lipophilic nature, you can select HLB scale. If you require WO or more oil soluble compound surfactant, then you can select between 0 to 9. And if you require water soluble or hydrophilic nature surfactant, then you select between 9 to 15 or maybe up to 18. This is all about HLB scale. And HLB scale of non-ionic surfactant whose only hydrophilic portion is polyoxyethylene is calculated using the formula. HLB is equals to E divided by 5, where E is a percentage weight of ethylene oxide. It's a formula for HLB scale. With the help of this formula, you calculate the HLB value. Next is importance of surfactant. Surfactant play important role in practical application products including detergents, fabric softeners, emulsifier, paints, additives, inks, and soil remediation and wetting. These are the application of surfactant. Means surfactant is also used for different industries other than enhancing solubility. And you can use surfactant is also for formation of a detergent, fabric softening. Means in some detergent you can add this surfactant for enhancing or improving fabric property and softening of the fabric. Next is emulsifier formulation. Next is paint. In paint industry, this surfactant is also used adhesive from tapes or adhesive like formulation. And inks, ink formulation is also contain surfactant. Some soil remediation and wetting property also have surfactant. This is large or broad range of use surfactant. So this surfactant is not only limited for your enhancing the solubility, but also for different industry, including different other than pharma or other than particular formulation. It is also for another purpose like ink, soil remediation, wetting, emulsifier, paints, additives, detergents, and fabric softeners also. Other than this, surfactants is also used as ski bags, snowboard bags, foaming, defoaming, laxative, agrochemical formulation, herbicides, insecticides, quantum dot coating, and biocides, the sanitizers, hair conditioner, and after shampoo and spermicides, novoxynol is example. Means this surfactant is also used for different formulations like foaming and defoaming property, for laxative use also, and for agriculture purpose like to act as a herbicide or insecticide, quantum dot coating, or hair conditioner, other spermicides. Means these surfactants are largely used in different type of industry also, like agriculture side is also used as to kill the some bacteria or herbicides or insects, and deforming and formic properties also, and different wax formulations. Next is effect of temperature, pH, and co-solvency. In this, you know about these three terms, how this pH affect the solubility, and how temperature affect the solubility, and co-solvency. What is co-solvency? In this effect of temperature, the solubility of a solute in a solvent is dependent on the temperature, nature of the solute, and nature of the solvent. When solubility of a particular drug is not only depend on the particular temperature, but also the nature of solute and as well as solvent. And when you react with solute and solvent, it forms the solution at particular temperature. And this temperature may be increasing amount or maybe decreasing amount depending on the type of the drug. Next is heats of solution represent the heat release or absorb when a mole of solute is dissolved in large quantity of a solvent. In this temperature change, they may be form exothermic or endothermic. Both reaction may be heat absorbed or resolved depending on the type of the formulation. This most of the substances are endothermic, absorbing heat in the process of dissolution. Means most of mainly these type of reaction or this type of process, the formulation mainly showing endothermic reaction, means absorb the heat in the process of dissolution. And when absorbing the heat, it shows more solubility or more easily solubilized property due to this endothermic reaction and absorption of the heat process. Next is for this substance, an increase in temperature results in increase in solubility. And in this also, you can say that when you increase the temperature, solubility is also increased. When you go to a higher temperature or at a heating temperature, the solubility is also enhanced. And exothermic substance heat off heat in process of dissolution, the solubility substance would decrease in temperature. Just opposite to endothermic reaction. In endothermic reaction, it increase the temperature, results increase solubility. But in case of exothermic reaction, you decrease the solubility or increase the temperature, just opposite. Because in this there is no heat absorbed. Care should be taken, heat may destroy or drug or cause another change in the solution. During this solubility enhancing method of changing the temperature, we should take some care that the temperature do not exceed the amount of increase or do not exceed particular limit. If it exceed in particular amount, it show some destroy or some instability of a drug, or maybe destroy completely that particular drug. So there may be some chances the drug may be destroyed. So you can maintain proper temperature instead of increasing continuously. You can check side by side how much temperature is required. This temperature is suitable or not for particular drug. Example, on excess heating the sucrose solution, it can get converted into inverse sugar. This is an example when you increase the temperature during heating of sucrose, it show invert sugar or just opposite sugar due to excess heating or large amount of a temperature. So you do not increase temperature continuously, you just control when a temperature required, enhance, or excessive heat may be destroyed at particular drug. And this next, depending on the type of reaction, whether it is exothermic or endothermic, heat is either dissolved or absorbed. And this mixture of chloroform and acetone, the heat proceeds by solute-solvent interaction, and much greater than the heat necessary to separate the molecule of acetone and chloroform, which can be directly rise temperature of liquid. Means in this, there may be chance that heat is released or this example of one is chloroform and acetone mixture, and you heat this and produce solid and solvent interaction, and with greater heat necessary to separate the molecule of acetone chloroform and can detect the temperature of the liquid. Next is application when heating or maybe enhancing the temperature or temperature change method. Pharmaceutical solution must be administered at a near room temperature, so it can be important factor to produce storage than the formulation. Increase the solubility of strength soluble salt and to increase the stability by reducing the moisture content. This temperature change is not only important for solubility enhancing, but also you can say that this is important for strongly soluble solute. Those who are insoluble or partially insoluble can change the temperature, get easily solubilized, show more solubility, as well as it also containing some moisture. So when you change the temperature, the moisture is also changed or maybe completely removed and show good quality, or excessive moisture can be removed. And other than this, you can start this temperature changing technique at room temperature, because during the storage it may be required room temperature condition. So first to start this condition at room temperature. Next is effect of pH in solubility, when how you change pH, or how effect of pH show at particular drug. In this, weak electrolytes undergo ionization and more soluble when ionized form, and degree of ionization depend on dissociation constant, pH of the medium. Means more ionized drug are solubilized easily, and weak electrolyte like ionized form are show more solubility and good drug compound which easily get solubilized. So in case of ionization process, you require ionized drug which easily dissociate, and other than this, solubility, the function of a pH is released to its pK, which leave ratio of ionized and ionized form of the substance. And this can be shown as pH is equals to pKa plus log A divided by HA. And if the substance is brought outside its pK, then the pH value where the half of the substance is ionized and half is not, and the solubility will be changed because we are introducing new intramolecular force, mainly ionic attraction. Means if you say that substance brought outside its pK or more than that particular pK, their pH value is half of the substance is ionized and half of not, and solubility will be changed because they introduce new intramolecular force, mainly ionic attraction. Only half of the molecule gets changed or half of the solubility gets changed in this condition. Example is COH has a pK value at pH around 4, and if pH is increased, then COH is converted into COO, and this may be interacted with H of water molecule. In this example, you can say that when we take COH as a pK value at pH around 4, and if we are taking this value for around pH 4, the pH increase, and when pH gets increased, the COH is converted into COO, and main molecule or interacted molecule is H with water. And the effect of pH on the solubility for weak electrolytes can be described by pH is equals to pKa plus log S minus S0 divided by S0, where pH is equals to pH below is the drug precipitate from the solution as undissociated form. S is the total solubility, S0 is the molar solubility of undissociated acid. This assures that a pH change for one single compound should not affect the other requirement of the product. In pH change method, during the solubility should assure that if you changing the particular pH or that particular condition, the pH changing do not affect your product or do not change their property. Suppose you enhancing the particular pH, it enhance the solubility but change their property also. If some interaction or maybe improper or unstable formulation. So during enhancing of the pH or changing of pH, you should know about it. It do not change the property of particular drug or particular product. It should be in a stable form. Example, chemical stability of drug may be depend on pH, and the pH optimal stability should not coincide with the pH of other ingredients, especially color, preservative, and flavor. Suppose you're changing the solubility with the help of pH, or by changing the pH, there may be some chances that you use color, preservative, and flavor. These type of excipient may interact with your formulation and show improper property or instability and change the property of particular product or formulation. So during this pH change method, cross-check the formulation is interacted with other molecule or not, like color, preservative, and flavors. Next is co-solvency. Co-solvency is another factor or another responsible property which also helps to enhance the solubility. To enhance the solubility of a poorly soluble material, the water miscible solvent are used. If the drug has a good solubility, the process of improving solubility is known as co-solvency. In the process, when you enhance the solubility or improve the solubility, this process is known as co-solvency. And this co-solvency mainly used for those drugs which are poorly soluble or completely insoluble material. With the help of certain type of solvent, to enhance the solubility or maybe improve the solubility. And this process is known as co-solvency. And the solvent that you use for particular formulation is known as co-solvent. The mechanism for solubility enhancement by co-solvency is not clearly understood, but it is proposed that solubility is increased by reducing the interfacial tension between the solvent or hydrophobic solute and decreasing the dielectric constant of the solvent. Means in this mechanism, you can say that there's a two compound or two solvent which helps to interact with each other, show dielectric constant property, reduce the interfacial tension between the two solvents. Due to interaction of maybe reduction of this interfacial tension, the drug get interact and show good property or maybe enhance the solubility. And in this, you can say that mechanism of solubility enhanced by co-solvent is not clearly understood. And nobody say that it is, this type of property is showing by co-solvency. We just assuming the property is available for this co-solvency, but in this solubility is increased by reducing the interfacial tension. Means you can say that when you add co-solvents, interfacial tension is reduced or show less interfacial tension due to this increase the solubility between the solvent or solute. Solute will be hydrophobic in nature and decrease the dielectric constant of the solvent. The commonly used acid acceptable co-solvent formulation of aqueous liquid for oral solution are ethanol, sorbitol, glycerin, and several membrane of PG series. These are the example which co-solvent or solvent is used for enhancing the solubility, like ethanol, sorbitol, glycerin, and several membrane of PG series you can use. When you use this solvent, the solubility is showing more for enhancing the solubility. You can also use this solvent in a combinations also. When you use this in a combination, show more solubility or more acceptable range of solution. For parenteral product, dimethyl acetamide is widely used, but in case of oral liquid, its application is limited because of its objection, odor, and taste. You can also change solubility of parenteral product by using the co-solvent. In parenteral formulation, but you take some precaution. Example, dimethyl acetamide is widely used for parenteral formulation to enhancing the solubility of oral liquid, and its application is limited because objection, odor, and taste. Means you can change the property of parenteral formulation, but you can also check or cross-check the other property. And in case of an oral formulation, maybe with the help of a co-solvent, the solubility is increased, but it's showing some odor or bad taste, and you can improve this odor and bad taste also for good formulation. Not only the particular solvent is responsible, but other parameters you also take, like to check odor and taste of particular formulation after adding co-solvent or after enhancing the solubility. Next is some characteristic of a co-solvent are used in the preparation is it must be non-toxic or non-irritating. During selection of the co-solvent, maybe in an individual form or maybe in a combination form, you should assure that that particular co-solvent is non-toxic or non-irritating. It do not show any side effect or any toxic effect or any harmful effect to a particular site or particular organ, or do not irritate that particular person. It means that if you are using one formulation, it have a good solubility, and this formulation may be good storage condition and overall good formulation come in the market. But when you use or apply that particular formulation, you use during storage, maybe during applying, it's a more toxic effect or more irritating effect, and less therapeutic effect. In this case, this is mainly occurred due to using of co-solvent. So you can select those co-solvent or those co-solvent combination which is showing non-toxic or non-irritating effect. It shows good formulation during the storage and maybe during applying, and overall good formulation for particular time limit, and do not irritate or do not show any irritating effect, redness, or any other side disease. It should be good in a proper manner, and it should be able to solubilize the drug in given solvent. The drug is completely solubilized. If you suppose dissolve paracetamol, particular solvent, it show more solubility, but it also precipitate out on maybe showing some accumulation of a drug, and your drug is not uniformly solubilized in particular solvent. So you should check or assure that your drug should solubilize completely in particular solvent or particular co-solvent. Next is should be cross the membrane. Means you just formulate a formulation, and after formulating, it show a good property to cross the particular membrane, or maybe easily cross that particular membrane. If you suppose prepare one drug which have a good property and good solubility, and it don't show any side effect and irritating effect, but it do not cross membrane, so no meaning of that particular formulation because it do not cross that membrane. If drugs do not cross the membrane, still in your blood or maybe in a particular site, and due to this particular site, it do not reach to required site and do not show that particular desired or therapeutic effect. So your drug should be cross the membrane by the help of the co-solvent, or when you use co-solvent, it do not affect the property and it easily cross the membrane. Apart from this increasing solubility, they are also used to improve the solubility of volatile constituent used in impart desired flavor odor of the product. If you use that particular compound for enhancing the solubility or increasing the solubility, in this case, you should know that improve solubility of volatile compound also. And in this condition, there is no changes of flavor and odor. It should be good flavor and odor. And yeah, all person take that particular formulation, because some formulation may change their color, odor, and flavor also. They are like no one take that particular formulation easily due to their odor or their fragrance problem. This is all about co-solvency. So today's lecture we covered all types of solubility enhancement method, effect of pH, effect of temperature, and co-solvency solubility. So after this complete lecture, you should know about this outcome, or you should know individual thing of that particular topic, like different solubility enhancement method, example, how it enhance the solubility. So we discuss already 6 to 7 types of solubility enhancement method, like temperature change, pH change, using of surfactant, co-solvency, dielectric constant, and individually. In surfactant, we discuss already HLP scale and different types of surfactant, ionic surfactant, anionic surfactant, and non-ionic surfactant. In ionic surfactant, we also discuss amphoteric surfactant, which is showing both the cationic and anionic as well as property. And next is application of a surfactant. In application of a surfactant, we already discussed different types of application. Means surfactant is not only used for pharma industry, as well as some other industry it is also used. Other than pharma, it may be used for ink preparation, maybe paints, or some foam or anti-foaming agents, or any other properties like both preparation and agriculture, like herbicide, insecticides, and pesticides. And HLB scale. In HLB scale, we can see that it is divided into hydrophilic and hydrophobic part, and it is divided into 1 to 9. And when you use hydrophobic in nature or lipid soluble in nature surfactant, then you select 1 to 9 surfactant HLB scale value surfactants. But in required hydrophilic or water soluble surfactant, then you select 9 to 16 or 8, maybe 18 up to HLB value scale. So you can decide which type of surfactant you require, either hydrophilic or maybe hydrophobic surfactant. According to the surfactant, you select 1 to 8 on 8 to 16 or maybe up to 18. Means 1 to 8 to 9 surfactant or HLB scale, showing that it's some more in lipid soluble or maybe in oil soluble in nature, or lipophilic surfactant. But in case of above 9 or up to 18, it's showing more water soluble or hydrophilic nature surfactant. So according to requirement, you select this HLB scale value surfactant. Next is effect of surfactant, temperature, pH, and co-solvency on solubility. All this is has to improve the solubility, not only solubility, but your formulation is also improve or show good property. But during selection of this technique, or selection of particular surfactant, or maybe selection of particular pH, you should assure that your formulation should be in a stable form during storage or maybe during administration or applying, because the solubility may be increased, but the formulation may be show instability, or during applying it maybe cross the membrane or showing more toxic effect and less therapeutic effect. So during selection of a technique or in particular excipient, you should assure about the overall formulation, or after a particular manufacturing of formulation, how formulation is stable for a particular time or particular condition, or it should show desired therapeutic effect at particular site also. This is all about outcome. So you should know this complete topic or different techniques, how you enhance the solubility of a particular drug, or different technique, which technique you use and which technique is more better, and how you decide which technique is appropriate for particular drug, and why you use this technique only. And you can also use by combination also, or for selection of a particular surfactant, you should take some precautions and properly check all surfactant, or during temperature changing, You check that you should maybe increase or decrease particular temperature. Not necessarily always require increase in temperature. Sometimes drug is dissolved in a cold condition also. So you take all this precaution during selection of a particular technique or particular excipient for the enhancements of solubility. This is the outcome. Now references. For references part, there are different references, but more good book or more important books are there some like pharmaceutical pre-formulation, the physical-chemical property of a drug substance by James I. Wells, Ellis, Harvard's Limited Publisher, Chichester, Ansel Pharmaceutical Dosage Form and Drug Delivery System, 8th edition by Lord B. Allen Nicholas, chief of which Howard C. Ansel, published by PA Publication Pvt Limited. And third publication or reference is for pharmaceutical pre-formulation by J.T. Partisan, published by Technical Publishing Co. And fourth reference is textbook of physical pharmaceutical by CBS Subramanian, published by Bella Prakashan. Next one is the theory practice of industrial pharmacy by Leon and Beckman, Habers, Lieberman, Joseph and King, third edition, published by Legacy Publishing House. And fifth one is Martin Physical Pharmacy, Pharmaceutical Science, edition by Patrick J. Simcoe, published by Liverpool William Wilkins. Sixth one is Pharmaceutical Dosage Form, Tablet, Volume 1, edited by Happers and Lieberman, Leon Lechman, published by Marcel Decker. All these are the good references for this topic. You can use this any book or maybe a combination of this book. Now the question part. In first question, the solubility of ionized parent compound. In this first option is optical counting method. B is equilibrium solubility method. C is intrinsic solubility. D is organoleptic property. In second question, the presence of a co-solvent can increase the solubility of hydrophobic organic compound. Option A is co-solvent effect. B is dissolution. C is capillary melting method. And D is organoleptic property. In third question, which property measure the resistance of a liquid to a fluid? A is density, B is viscosity, C is volume, and D is solubility. And in fourth one, what is the correct definition of the solubility? Correct definition of the solubility, A option is the ability of a solid particle to disperse throughout the liquid in a continuous phase. B option is ability of a solute to dissolve into a solvent. And C option is the rate at which solute dissolve into a solvent. And D option is the ability of immiscible liquid droplet to disperse within the second phase. And fifth question, which form of the drug has the highest viability? A1 is coated tablet, B is solution, C is tablet, and D is emulsion. And sixth question, why emulsion dosage form the lipophilic drug provide better? A option is easy manufacturing, B option is higher stability of the drug in emulsion form, C option is presented a large number of oil to the GIT for the absorption of the drug, and D is the fast clearance from the plasma. And next, seventh question is, in the stability of emulsion, which important instability step should be prevented? A is breaking, B is cosense, C is flocculation, D is creaming. And in eighth question, downhill movement of particle in suspension causes assist segmentation, promote segmentation, prevent segmentation, and D or last option is increase segmentation rate. In ninth question, which of the following excipient may be used to limit the presence of microorganism in liquid formulation? A is purified water, B is sodium lauryl sulfate, C is benzene chloride, D is ascorbic acid. In this question or option, you can see that there is a different type of surfactant. In surfactant, you can also use as a preservative. According to suitable type of preservative, you select any one out of A, B, C, D. And in last 10th question, what is the role of xanthan gum within some liquid formulation? A1 is regulate pH, B1 is control viscosity, C1 is enhance solubility, D1 is enhanced stability. All these are the four options A, B, C, D, and you select any one option for this correct answer. And this is all about 10 question of this topic. And thank you so much for listening and watching this video. Thank you.